Good morning. I have at least, well, close to half the class here. That's surprising. All right, analysis technique. Let's go to the right section first. So we stopped here, load line analysis, and then I introduced, I believe, the ideal diode model. So let's continue with the ideal diode model, and we'll finish up today's class with all of our analysis techniques done. All right, so ideal diode model, just as a brief recap, we simply break up the diode characteristic, the nonlinear characteristic, into two parts. And we say when the diode is on or forward. So when the diode is forward biased, we say it's on, and we replace it with a short circuit. And when the diode is reverse biased, we say it's off, replace it with an open circuit. In the forward bias, a result would be that the diode voltage is 0. And in reverse bias, of course, diode current is 0. Also, for forward bias, as a result of the diode voltage being 0, we can say that the current must have some positive value, greater than or equal to 0. And here, VD would be less than 0 or negative. Remember, VD is always measured with a positive reference at the anode. So when you refer to diode voltage, you're always referring to the diode voltage as measured at the anode with your reference at the cathode. Positive reference always at the anode. Okay. So if the diode is reverse bias, VD must have a negative value. Make sense? Any questions? Yes. It's if we say reverse bias, it's automatically mathematically when you put down equation, it'd be minus. Yeah. The question being asked is whether we put a negative or not. Yes. So if it's forward bias, we refer to everything as positive. If it's reverse bias, we refer to as negative. So typically, if you read in the books, sometimes some authors, or when you talk to other people, sometimes the assumption is already implied, because if it's reverse bias, it's always negative. Mathematically, we put a negative sign in front of it. Okay. So we replace it with a short circuit in forward bias, open circuit in reverse bias. If we take a look at our circuit, the original circuit we had was one voltage source, one resistor, and one diode. So at the beginning of our analysis using this technique, what we do is we make assumptions. We don't know what the state of the diode is. So we assume the diode is either on or it's either off. Okay. But the assumptions, yeah, engineers are free to make whatever assumptions they want. But of course, the assumptions are based on certain logic and rules. Meaning, for example, if I know and I can see that the cathode is connected to the negative end of the power supply, more likely than not, the diode must be off. The diode must be on. Right? Anode is higher potential than the cathode in this circuit. So logic dictates that the diode is most likely on. So my assumption would be that the diode is on. If I assume that the diode is on, I can then perform an analysis by redrawing the circuit. Then the analysis, I would verify whether VD, diode voltage, is equal to 0 and whether ID has a positive value. If those conditions are true, then my assumption is also true. If it's not, you go back to the beginning, you change your assumption, and you redo it all over again. Okay, so it's kind of like a flow chart. You have a diode state, yes, no, right? If it's a yes, then you proceed with your analysis, on or off. Then you proceed with your analysis. At the end of your analysis, if your answer must match up with your assumption, yes or no. If it doesn't match up, then you go back to the beginning, you change your assumption, and you redo it again until you get a yes. Does that make sense? Take 10 seconds. Let me know if you have any questions. Any questions? Oh. Okay. So then if my diode is assumed on, I replace it with a short circuit. Diode voltage VD must be 0 volts. And ID must have a positive value. So I assumed a state. I replaced the diode based on that state. In this case, a short circuit. Now I calculate the value for ID. In this case, of course, it's rather straightforward. ID is equal to 10 minus 0, which is the diode voltage, divided by 10,000. So 1 milliamp. And it's a positive value. So my assumption is valid. My assumption is true, and it is valid. So I assumed the diode is on, and my assumption is verified. Okay. Let's take a pause. Let me know if you have any questions. Does it make sense? Okay. What if the diode was connected opposite way? Meaning like this. What would my assumption be? What would you assume the diode is? What state is it in? Is it forward bias? Is it reverse bias? Reverse bias, yes. You will assume the diode is reverse bias. And so assume D is off. And I can replace with the open circuit. Which means my diode voltage must have a negative value. So let's perform the analysis. Quite obviously, the current ID is equal to 0. So at least one is verified. Let's see if the other is verified or not. And in this case, it's rather straightforward. Apply KVL around the loop. And you can find VD is minus 10 volts. Right, VD is minus 10 volts. So VD has a negative value. So my assumption is valid. Okay. As I said, this is a straightforward example. You got one diode, one source, and one resistor. So it's easy to analyze. So the technique overall is used or utilized when we wish to perform a very quick analysis. And when I say quick, it is relatively quick. It's not as if it's get done within like a few minutes. It's just relatively quicker than the other analysis techniques, and particularly useful when you have more than one diode in your circuit. Okay, so if you have multiple diodes in your circuit and you wish to perform a quick analysis, this is the technique we would use. And to give you an idea, if you have n diodes, each diode has two possible states. So it's kind of like the binary number system. Total number of states is equal to 2 raised to n. If it's one diode, you make an assumption on or off. If you are correct, great, you obtain your answer in one analysis. If it's incorrect, you go back, you change your assumption, perform your analysis a second time. So you have to perform two analyses for one single diode. If it's two diodes, you now have four different states, four possible combinations. You have to make an assumption about both diodes. You go through your assumption, go through your analysis, see if it's correct or not. Otherwise, you have to redo it again. You do it once, twice, thrice, maybe even four times. But if you're doing it four times, then you probably don't understand them. Then I probably would not be understanding the circuit correctly. The reason is, if you have a circuit with like two diodes or three diodes, depending on the circuit configuration, I can use certain logic to make those assumptions. So in this case, in this circuit, the cathode of my diode was connected to the negative end of the voltage supply. So my assumption is the diode most likely is on. So when we look at a circuit, I would make an assumption based on the circuit configuration. If the negative end of a supply or the cathode, let's say, is decidedly connected to the negative end or is lower than the anode, then the diode most likely is conducting and is in forward bias. If the anode, however, is lower than the cathode, it's most likely reverse bias. So even though there are multiple states that are possible in a circuit, you make those assumptions based on certain logic and rules. Otherwise, you'd be performing multiple analyses all day long. Does that make sense? Right? So 2 diodes, 4 possible states, 3 diodes, 8 possible states, 4 diodes, 16, 5, 32, and so on and so forth. So there is an example with like 3 diodes that we will do, and not today, but most likely Friday. And I will make an incorrect assumption in there at the beginning, just so you can see how we can try and solve it. Okay, 10-second pause. Let me know if you have any questions. Okay. So then we have an extension of the ideal diode model, which is known as the constant voltage drop model. The constant voltage drop model, we are adding in the turn on voltage to the ideal diode model. Okay, we're adding in the turn on voltage. The turn on voltage, of course, we call it V on or VTO. For silicon, it's about 0.6 or 0.7 volts. Germanium, it's about 0.2 volts. How about for gallium arsenide? Anyone remember from lab yesterday? 1.2 volts. Anyway, So we add this voltage that is required to turn the diode on. We don't change anything else. The only thing we are changing is we are shifting the characteristic to the right. We're shifting the forward bias characteristic to the right. Okay, that's all we are doing. Oh, there's one more point mention about the ideal diode model is that we are breaking up the non-linear characteristic into pieces. Forward bias and reverse bias, they are now two linear pieces. And so this technique is also known as piecewise linear. The nonlinear characteristic as a whole, but we break it up into two different pieces, forward bias, reverse bias, and both pieces have a linear relationship. Hence, it's also known as piecewise linear. Okay. So constant voltage drop model, we are shifting the forward bias piece towards the right by the amount of the voltage. So 0.6 volts. And the only thing we change is the forward bias characteristic. We insert a power supply. That power supply represents the voltage that is required to turn it on. Okay. Positive terminal is at the anode, negative is at the cathode. So in the ideal diode model, we replaced it with a short circuit right here, and we replaced it with a short circuit. In the constant voltage drop model, we replaced it with the power supply, not a short circuit. The power supply is required to turn the model on. Everything else about the technique remains exactly the same. That doesn't change. So it's exactly the same as the ideal diode model. We make an assumption at the beginning. We analyze the circuit based on our assumptions. Then at the end, we look at our solution. Does it match our assumption? Yes or no? Yes, that's great. You're done. No, we go back to the beginning. We change our assumption and we redo the analysis. Okay. And the only difference is add on the voltage. So if we take our example again, we would replace it with 10 volts. This is 10 volts. This is 10K. You replace the diode with a voltage. Thank you. So this is let's say it's silicon diode, so it's 0.6 volts. And this is 10 kilo ohms. Everything else remains the same. We are assuming a forward bias diode. So if it's a forward bias diode, it must be conducting. If it's conducting, a current should be flowing through it, and that current should have a positive value. I can write a equation around the loop and get 10 minus 0.6 divided by 10,000, and I obtain ID as 0.94 milliamps. Positive value for ID, therefore my assumption is valid. Okay, assumption is valid. All right, let's take a pause. Let me know if you have any questions. Do the steps make sense? Okay. No questions? Everybody understands everything? Well, then let's have a pop quiz. Yes? No? Okay, so let's look at the last of our 4 techniques, the mathematical model. Okay, mathematical model is straightforward. We are using the diode equations and then, of course, deriving a secondary equation from our circuit. So let's draw out our circuit. We have plus minus VD. And we have the diode current flowing through the circuit. So mathematical model is straightforward based on the diode equation. So the diode device equation is ID is equal to IS times E raised to VD over VT minus 1. I'm ignoring the N, the non-linearity factor, because it's 1. And in most cases, it will always be 1. Okay. So if N is not given or explicitly stated, always assume it to be 1. Okay. Right now it's given and it's 1. So I'm simply ignoring that in my equation. And then, of course, the diode voltage equation is VT times log of ID over IS. And I'm going to ignore that, because that 1 is going to be insignificant compared to the rest of the terms. Okay, so just simplifying it. As an engineer, it's your choice. Depends on what kind of values you need. If you need an exact value, then you want as many variables in there as possible. If you just need an approximate value, you can eliminate as many variables as you want. Okay, so in this case, N is equal to 1. We need to write that one. And then, of course, the last term on the right, minus 1, is going to be insignificant compared to the exponent. Okay, so these are the 2 device equations, right? Solely for the diode. Now, when you take the diode, plug it into a circuit, we need secondary equations so we can analyze the circuit and derive our secondary equations, right? Similar to what we did with the load line. So here I can write an expression. I can write an expression for the current flowing through the circuit, right? So a secondary equation for ID. And ID is equal to 10 minus VD divided by 10,000. Right, so that's a secondary equation that has, again, 2 unknown variables, ID and VD. Okay, ID and VD. Remember, same with the graphical analysis, right? We had a device characteristic curve, but 2 unknown variables. So we drew a secondary line in there, and we call it the load line. Intersection point gives us, intersection point of the 2 gives us the solution to the diode values. We're doing kind of the same thing here, but just mathematical calculations. We have the device equations, and then we are writing a secondary equation from our circuit. Now, both of these have VD and ID. Okay. What we can do is we can plug either VD in here, or we can plug ID in here. Right? We have 2 equations for 2 variables. You plug in either one of those into the other expression, you can eliminate one of them. If you plug in VD into ID, then the entire expression only has ID. If you plug in ID into the equation for VD, then you only have VD in there. Does that make sense? Or am I making sense? We have an expression for ID. That expression contains VD. If you plug that expression into this right here, meaning this specific term right there, we can eliminate ID from our expression. We only have one equation in terms of one variable. So this is how it would go. We have VD, VT times ln, natural log of ID over IS, and then ID is now replaced with 10 minus VD over 10,000 divided by IS. Does it make sense now? Right. So now we have eliminated ID from there. Only thing we have is VD. Let's simplify it a little bit further. Okay. So that's where things stand. We have VD on the right side, and then we're saying it's equal to some equation, but that equation also contains VD. And it has a transcendental function, which is the log. So it's a transcendental equation, does not have a closed form solution. So it's kind of like the iterative, it's kind of like the similar to the previous where we make assumptions. So here's what we do. We do an iterative calculation. We have VD equals to something that is also a function of VD. So we choose a value of VD, we calculate the right side of the equation, and then we see the end result. Does it match up to our original assumption of VD? If it doesn't, then we take that value and plug it into the right side equation. We calculate again. We keep doing it again and again and again until our final value matches up with our assumption. And that is known as an iterative analysis. So in iterative analysis, we are not quite throwing things at the wall to see what sticks. We pick a starting point in educated guess. So choose a starting value for VD. Then, this statement by itself in isolation would not make sense. Calculate VD. Choose a value for VD and then calculate VD. Okay, but you're choosing a value for VD for the right-hand side, calculate it, and then match it on the left-hand side. Calculate VD. Does calculated VD match the assumption? Stop when it does match. Okay. So let's take a 10-second, actually we take a 10-second pause, write it down. Let me know if you have questions. On the next slide, you will see how easy it is. Or at least not easy, but straightforward. Okay. So far, so good. So this is programmed, or not programmed, but done in a spreadsheet in Microsoft Excel. You simply make assumptions. So this are my assumptions or assumed values for VD. And then this is, of course, simply just programming the equation in there. This is the final answer, obviously. This is the entire equation. VD is equal to log of B minus VD times divided by R times IS times VT. So as a starting point, you always want to make an educated guess, right? So educated guess means if this is a silicon diode, and I'm assuming that the diode is going to be on, then the diode voltage should be somewhere between 0.6 and 0.7. Y'all with me so far, right? So when I wrote down here, choose a starting point, choose a starting value for VD. As a starting point, if it's a silicon diode, I know it has to be somewhere between 0.6 or 0.7. So you can pick 0.6, you can pick 0.7, pick 0.65, doesn't really matter. Okay. So here, if you look at the second value right here, I choose my starting as 0.65. I'm choosing VD is equal to 0.65. I plug it into the equation and I calculate the value for VD. What do I obtain? Do I obtain 0.65? No. Since I didn't obtain 0.65, my answer is not quite correct yet, but it's close. It shows me as 0.592. So I take this 0.592 and use it as my assumed value for the next iteration. And then I perform the calculation. I obtain 0.592. Not quite exactly the same. So I would take that, plug it into my assumed value again in column 1, do an analysis, and again obtain 0.592. And now we are exactly the same up to 6 decimal places. Plug it in again, and now I'm obtaining exactly the same value after that iteration. This is a calculated software, so it's very easy. Once you type out the equation, you just simply drag it down. In 1 second, you have your answer, right? Within a few 5 steps. If I was doing this manually, and I was doing it, let's say, up to 3 decimal places, I would have had my answer right here in the second step. 0.592 gives me 0.592. So my model has converged. When my calculated value matches my assumption, we state it as my model has converged. And my solution is now correct. Does that make sense to everyone? And this is, again, just done in Excel spreadsheet. You can use MATLAB, any kind of mathematical software to program your equation, and it'll easily do an iterative analysis. Okay, so this is a very real thing. You would be doing this as a working engineer, working professional, often, depending on what kind of job you go to. Okay, but does the iterative analysis make sense? We obtain an equation. It's a transcendental equation, cannot be solved directly. So we pick a starting point. We choose a starting value, calculate it, and then see if it matches with our assumption. And just for kicks, I entered 0 in there as my starting point. Even though I know diode voltage must be at least 0.6 volts, I entered 0 in there just to see what I get. If you enter 0, you obtain 0.594. And I should have actually entered 0.594 in there just to see how many steps it takes to get to my final answer. But I'm guessing not very long, because 0.594 is very close to 0.12, right? So probably like 1 extra step. So if I plug in 0.594 here, more likely than not, I would have obtained 0.592. Make sense? Right? So again, you can pick any starting value you want, but you have to keep performing your iteration until you obtain your analysis. Now, all equations may not give you or may not converge all the time. It is quite possible that it may never happen. Then you'd have to write a different equation and see if it works out or not. Okay. All right, let's take a pause, maybe a longer pause, but think over it and let me know if you have any questions. Yes. 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 Okay, so if I understand your question correctly, the question being asked is, why did I go all the way down here? Oh, yeah. So we could take this. It depends on our application. Depends on how much tolerance we would like in our system. So stopping. So your question is why or how and why do we stop at a particular value? The answer is depends on the application. So if I wanted like the exact number, I would take one more step and I would stop right here. Because after that, it's the same for up to what? 8 digits, 8 decimal points. It's exactly the same. But also to answer your question, I could have possibly stopped right here. There's 3 decimal places. It's the same, 0.592. So if I was performing this manually, which I did back in the day, 30 years ago, I would do 0.592. Assume 0.592, plug it in, and you obtain 0.592. I'm done, right? Uh-huh. Well, we can't settle. So I think the point you're making is, can we just stop right here? But we don't know if it's 0.594. So we plug 0.594 back into our starting point, and then we run the calculation again. If we obtain the exact same value, then we can say, okay, now we are done as our assumption. So we make an assumption, we calculate, and then we see if our assumption, if it matches our assumption or not. Yes. Mm-hmm. 0.594. Yes. No, if I get 0.594, because it flows down, right? So if it's 0 and I obtain 0, maybe my answer is correct, 0 to 0. But if I plug in 0 and obtain 0.594, now I'm going to plug 0.594 here, see what my answer is. And if that 0.594 stays 0.594, then my assumption is correct. But 0.594 changes to 0.592. Now you have a decision to make. Do you want to go up to 2 decimal places, or do you want to go up to 3 decimal places? If you choose 2, then your answer is valid. If you choose 3, then your answer is not valid. Then you perform one more step. So now you plug in 0.594 again, obtain 0.592. When you plug in 0.592, you obtain 0.592. Answer is correct. Then you stop. So again, if it's 2 decimal places, you're done in 2 steps. 3 decimal places, you're done in 3 steps. And then if it's 4, 5, 6, 7, or 8, then it's 2 more steps. So again, depends on your application, depends on the end result that we want. Okay, so that's a personal decision based on your application. Does that make sense to everyone? Okay. And again, as I said, you can use, on any online solver. You can use MATLAB, program the equation in there, and you can let it do the work. Okay. So 4 different analysis techniques. Let's compare the results. Load line. Remember, graphical analysis, we chose, and I stated we could possibly state it as 0.95, but more likely it was slightly less than 50%, so I chose 0.94. 0.94, mathematically, I obtained 0.941. Once I obtain my voltage is 0.592, you plug it into the diode equation, and you find a value for ID. The value for ID came out to be 0.941, very close to my graphical analysis. Okay. Then constant voltage drop model, 0.94, right? Because we chose 0.6 as our voltage drop. If we choose 0.7 as a voltage drop, our current would be 0.93. Does that make sense? See, these are all techniques to use as an engineer to predict what voltages would appear in your circuit when you measure them. Okay. None of them are incorrect. They're all correct and valid. Well, except for the ideal diode. Again, that's the ideal condition. So, but even that is not too far off. 1 volt versus 0.94, right? Less than 10%. Does that make sense to everyone? Right? So in the ideal diode, of course, voltage VD would be 0. So that's far off, but the current is not too far off. And the rest of the other three are very close. 0.6, 0.6, 0.592, and then 0.94. Right? So no matter which model you use, if you perform it correctly, then your answer, you'll be able to predict your actual experimental values using any of these models. Okay. Excuse me. All right. Any other questions? Okay. So for now, there is another example of solving circuits with multiple diodes, but I don't have enough time to get into it today. So what I want to do is introduce diode rectifiers. Okay, diode rectifiers. Now, everything that runs on electricity in this world is more likely than not DC, especially everyday consumer devices, right? Everything that you see around in this room, this monitor, this display tablet, writing tablet, the projector, smartphones, tablets, televisions, everything runs on DC. But all of power generation and distribution is done on AC. Okay, is done on AC. So going back, going on a little bit of a tangent. AC power generation and transmission. Generation is very easy in AC because you have a rotating electric. You have a rotating electric field inside a rotating coil inside a magnetic field. So it's moving between a north pole and a south pole. So by its very generative nature, it is alternating. Okay, so it's very easy to generate an AC voltage compared to a DC. Plus, transmitting it over long distances is possible because of the invention of a working transformer. So these transformers are 2 linked inductive coils. And back in the late 1800s, there were 2 Hungarian researchers, 2 or 3 Hungarian researchers that were credited with the invention of a working prototype of a transformer. Okay, there's lots of research been done with lots of people, but anyone who brings it in a working form to a market usually gets the credit. Another person who gets a ton of credit for working with AC generation and power transmission is Tesla. He worked a lot with inductive coils, magnetic inductive charging, wireless charging, wireless charging that you use in your phones and tablets nowadays. That's all attributed to him. So the AC transformers allow us to step up or step down our voltage with ease. Okay. And the reason it's important is because AC power is transmitted over very long distances. So at long distances, even the conductor that is used for the transmission lines will have some resistance. This is hundreds of miles, perhaps tens of hundreds of miles, right? So when you're transmitting over such long distances, it has resistance. When you have resistance, you have power loss. So you're transmitting electrical power from point A to point B, a huge amount of losses that take place. Electrical power is the product of voltage and current. In terms of resistance, it is V squared over R, or I squared times R. If your resistance increases, your power loss increases. So you can either increase the voltage or you increase the current. But if you increase the current, then your power loss is the squared of the current. So a huge amount of losses. So it is easier by far to increase the voltage when you send it over long distances. It is very easy to do so with transformers. So they generate the voltages in tens of hundreds of volts. They step it up to tens of thousands of volts, 10,000 volts, 20,000 volts, 30,000 volts. Send it over long distances with minimal losses. And then you step it down when it gets to the consumer. All around campus, you may have noticed, actually right around the corner of this entrance, there is a electrical woodshed. Danger, do not enter. So there's a transformer in there, high voltage transformer, I believe, in there. If you've walked down a residential street, you might see light poles, power electric poles, and there are circular devices on them, right? Those are transformers. You've probably seen one in the power lab on the other side, sitting on the floor. Maybe you'll take an EE295, right? So you've seen that sitting on the floor, that transformer. Anyway, coming back to where it pertains to us. So all of transmission of electricity, electrical power is in AC. But when it comes to us, we need it to be DC. And that's where our humble diode comes into the picture. A diode is a one-way street. It conducts current only in one direction. Alternating current goes up, down, in multiple directions. In two directions. And so if you place a diode in front of your device, then the AC is fed into the diode, but it only allows DC to come out, or at least pseudo DC to come out, because it's only conducting in one direction. Okay. And so that circuit is known as a rectifier, because it's rectifying from AC to DC. Okay. Everything that we use has a rectifier circuit built in. So this display, this writing tablet, the projector, everything has a diode rectifier circuit built in. Every charger that you use, laptop charger, laptop adapters, your cell phone chargers, tablet chargers, they all have diode rectifiers built in. Ever hear of wall warts? Wall warts? Not missing out on much. Wall warts were AC to DC rectifiers, kind of heavy, size of my fist, fit in our palm of the hand, and they would plug into the wall. So anywhere you went, whether it was your homes, residences, workplaces, you'd have devices that were connected to the wall using these kind of chargers. So think of them as heavier versions of your cell phone or tablet chargers that you plug into the wall. Okay, they were heavy because they each contained a transformer. The transformer would step down the AC voltage from 110 or 120 volts down to like a usable voltage of 10-15 volts. And that 10-15 volts AC would be fed into a diode. The diode would convert it or rectify it into DC, and that DC would then plug into your device, which is still what you have with your laptop adapters and your chargers, except now with design and with better functioning transformers, the AC is directly converted to DC at hundreds of volts, and then it's converted back. It's stepped down, DC to DC conversion, and then it's stepped back up. Sorry, not step back up. It's then converted back into AC. So now the transformer size is very small, and that's why it's lightweight. So the circuit is exactly the same as a original wall wart, except now it's directly rectified at high voltages. I had cracked open one, so I had somewhere in one of my in my office in one of my boxes. If I find it, I'll bring it to class next time. So we'll end class here today, and I'll see you all on Friday.